scanning the whole sample. It gives us a peak here, then comes down here, then gives us a peak here. So what happens in between? This is important to know. Atoms are behaving as scattering centers, right? Keep that in mind. I am coming to that point later. I have again shown here that distances are larger in real space and the reciprocal space. The distances are shorter, and 2 pi by b is the k, as I showed you in the previous slides. And 2 pi by a, 2 pi by b along the a and b lattice parameters. And here the diffraction pattern, and here the real lattice. Similarly, in the reciprocal lattice, you use stars to reciprocate, to show the reciprocal of the distances. Then the choice of the unit cell. Because if you look into it, here, unit cell, one lattice point per unit cell, we call it primitive. And if it has more, then it is non-primitive, right? So this is again your choice. And the lattice parameter, ABC, which people call for certain materials that these are ABC. They are not from Torah or other book. People have measured them. So they call the unit cell as this or that. And according to that, they measure the ABC. But if instead of that, your choice is this. This is another smaller cell, right? So you have all the possible choices of arrangement of atoms and a unit cell. You go for primitive option, you go for non-primitive option, you go for cubic, tetragonal, and whatever structure possible there are. Then you refine it. You refine it, and that refinement leads you to the final decision. There are many people who are still studying the structure of calcium titanate, after which the whole family of ABU3 type compound is known perovskite. It is such a known structure, but still people are working on that. That were they correct when they give this specific structure to this material? So if you can find another option, a better option, by all this I mean that this is your choice to select a unit cell. And they are not from nature or something like that. People have said that this unit cell is like this. If you have another option which is more reliable and scientific, then you can publish that, and you have done a great job. That the mistake which people were doing for many years, you corrected that. So people are refining structures with the development of new techniques. Here, the atomic packing fraction. It is very important that you cut various atoms for various structures, and from there you determine the volume of atoms in a unit cell divided by the volume of the unit cell. So this tells you about the filled space and the difference between the filled space and the unfilled space, right? So If the packing fraction is less, then obviously the density will be less or more. When the spaces are less, the density will be more. When the spaces are more, non-occupied spaces, then the density will be less. And this is the way how people calculate it. Look at this, because it mostly appears in examination papers that how people calculate it, right? The atomic packing fractions for various crystal symmetries. Similarly, atomic packing fraction for BCC is calculated like that, and for FCC it is calculated as 4/3.5A cube. A little bit moving forward, I think most of you know this, I am just repeating it, that a plane intersects the x-axis at 1. By 1 here we mean 1 lattice parameter. And the one here is along the x-axis is A, right? So when it is intersected at A, at 1, and the y and z axes are not intersected, so it is parallel to the y and z axes. This means they are intersected at infinity, are not intersected. At infinity means no, right? So when they are not, then you take reciprocals, 1/1, 1/infinity, 1/infinity, and this gives you 1, 0, 0, which are the Miller indices of that plane.